Welcome, curious minds, to another deep dive. Today, we're peeling back the layers on a concept that's, well, literally foundational to our modern world, yet often invisible: bending.
Yeah.
How do bridges stand firm? How do buildings, not collapse? It really all comes down to understanding how materials and structures respond to forces that make them curve or sag or flex. Our mission today is to equip you with the core insights and maybe some surprising facts to truly understand how beams, those silent workhorses of construction, behave under load.
That's absolutely right. I mean, imagine trying to guess where a bridge might crack just by looking at it. It's practically impossible without this knowledge. This isn't just about definitions, like you said. It's about giving you a true feel for the why and how behind everything. From the floor you might be standing on right now to the deck of a bridge you drive across, or even the wing of an aircraft soaring overhead. It's really a fascinating journey into the hidden mechanics of, well, everything around us.
Okay, let's unpack this then. When engineers talk about bending, they're primarily talking about what happens to a beam.
Mm.
So, what is a beam exactly? Can you break that down simply?
Sure. Think of a beam simply as a long, straight piece of material, like a floor joist in your home, maybe. It's designed to carry weight pushing down on it, sort of perpendicular to its length, not pulling it from the ends.
Right, not like a rope being pulled taut, more like a plank bridge.
Exactly. And they're everywhere, playing this absolutely crucial role, supporting building floors, bridge decks, aircraft wings. It's fundamental.
It really is a marvel of engineering we often take for granted.
Absolutely. And these beams, these essential elements, they come in a few basic configurations. It mostly depends on how they're supported. The most common is probably a simply supported beam. Just picture a plank laid across two supports, maybe pinned at one end, roller at the other, like a basic bridge.
Okay, simple supports. Got it.
What else? Then there's the cantilever beam. This one's fixed really firmly at one end, but the other end is just free. Think of a diving board or maybe a balcony sticking out.
Ah, right. Fixed at one end, hanging out there.
Precisely. And finally, the overhanging beam. This is sort of like a simply supported beam, but one or both ends extend freely beyond the supports.
Okay, so different ways to hold them up.
Yeah.
But what's the big challenge for engineers dealing with these?
The fundamental challenge is figuring out the internal forces that develop inside the beam because of the loads on it. We call these shear force, that's sort of a slicing force and bending moment, which is the twisting or bending effect. And the critical thing, the really key part, is that these forces aren't constant. They change all along the length of the beam.
They vary from point to point. Okay, so if these forces inside a beam are constantly changing, how on earth do engineers map them out? Is there like a special tool or method they use to visualize this?
That's exactly where shear and moment diagrams come in. These aren't just, academic exercises you do in school. They're like x-rays for beams. They give you detailed visual information about how that internal shear and bending moment vary along the beam's axis.
X-rays for beams, I like that. So this X-ray vision helps them make smarter decisions.
Absolutely crucial decisions, like
Wow.
knowing exactly where you need to put reinforcing steel in a concrete beam, for instance, or figuring out how thick or deep a beam needs to be at different points along its length to handle those changing forces.
So how do you even begin to create these visual maps? Is it complex math?
It starts with math, yes. Engineers usually begin by expressing the shear, we call it V, and the moment M as functions of position X along the beam. You typically set up your coordinate system, say, starting at the left end. And you have to realize that these functions might change abruptly. Wherever a load is applied, a heavy weight, or even the start or end of a distributed load, you might need a new function for the next section of the beam.
Ah, so different equations for different parts of the beam, potentially.
Exactly. And to make sure everyone's reading the map the same way, there's a standard beam sign convention. It's just an agreed upon way to define what's positive and negative. For instance, a positive distributed load is usually shown acting upward. Positive internal shear makes the beam segment want to rotate clockwise. And here's a handy one for bending moment. A positive internal moment causes compression in the top fibers. It makes the beam segment sort of cup upwards like it could hold water.
Hold water. That's a great visual. Easy to remember. And here's where it gets truly fascinating for me reading through this. These fundamental differential relationships engineers discovered. They seem almost like magic. The slope of the shear diagram at any point actually tells you the intensity of the distributed loading right there. That's dV dx equals W1.
Correct. It's a direct link.
And even more powerfully, the slope of the moment diagram is equal to the shear force. dm dx equals V. So if you know the loading, you instantly know something about the shear diagram's shape. And if you know the shear, you know about the moment diagram's shape. It's elegant.
It is incredibly elegant. And building on that, these relationships also extend to the areas under the curves. The change in shear between any 2 points along the beam is precisely equal to the total load, the area under the load diagram in that region.
Okay, so the area tells you the total change.
Exactly. And similarly, the change in moment between any 2 points is equal to the area under the shear diagram within that same region. This allows engineers to graphically construct these diagrams. Sometimes you can sketch them out quite accurately just by understanding these slope and area relationships without solving complex equations for every single point. It's a really powerful graphical method.
It really sounds like a sophisticated visual language for understanding these hidden forces. And you mentioned jumps earlier. You can actually see these relationships in action on the diagrams, right? Like a concentrated force.
Definitely. A concentrated force, think of someone standing on a specific point on a plank, causes an immediate sharp jump straight up or down in the shear diagram at that exact point.
And a twisting force. Couple moment.
A couple moment, if one is applied directly to the beam, causes a sudden jump in the moment diagram. Not the shear, just the moment.
Wow. So the diagrams really paint a picture of exactly what's happening and where.
They do. Engineers learn a systematic procedure. Figure out the support reactions first, how the supports push back, then define the internal shear and moment functions for each distinct section of the beam, and finally plot those functions. The textbooks are full of examples showing how this works for all sorts of beams and loads, using both the direct function method and this graphical area slope method.
Okay, so that's the forces inside the beam mapped out.
Yeah.
But what about what happens to the material itself? We said it bends.
Mm-hmm.
How does it actually deform?
Right. Let's shift focus from forces to deformation. It's quite interesting visually. If you imagine drawing a grid of horizontal and vertical lines on the side of a beam before bending it, when a bending moment is applied, those original horizontal lines become curved. No surprise there. But the vertical lines, remarkably, they remain straight. They just rotate. They stay perpendicular to the curved horizontal lines.
They stay straight. That seems counterintuitive.
It does, but it's a key observation that simplifies the analysis immensely. And this leads us to a crucial concept: the neutral surface. Imagine a layer, a surface, somewhere inside the beam running along its length where the material isn't stretching or compressing at all when the beam bends.
So it's just neutral.
Exactly. That's the neutral surface. And where that surface cuts through the beam's cross-section, that line is called the neutral axis. It's like the beam's calm center in terms of stretching or squashing.
Okay, the neutral axis. And engineers make some assumptions about this, right?
Yes, a few key assumptions to make the math tractable. First, that central line, the neutral axis itself, doesn't change length. Second, as we just mentioned, those cross-sections remain plane, they stay flat, and they remain perpendicular to the now curved longitudinal axis during bending. And third, there's a minor effect called Poisson's effect. When you stretch something, it tends to get thinner in the other directions.
Right, like a rubber band.
Exactly. In beams, these tiny side-to-side strains are usually so small compared to the main bending strain that engineers can often safely ignore them, especially for basic analysis.
Okay, those assumptions seem reasonable. And they lead to, what's the core insight about the deformation?
The core insight is this: the amount of stretch or compression, what we call longitudinal normal strain, varies linearly with the distance from that neutral axis. Think of it like a ramp. Zero strain right at the neutral axis. Then, as you move away from it towards the top or bottom surface of the beam, the strain steadily increases, linearly. It reaches its maximum value right at the outermost edges, the fibers of the beam.
Linearly. Okay, so it's a predictable pattern. Zero in the middle, max at the top and bottom.
Precisely. And because strain is related to stress, assuming the material is behaving elastically, following Hooke's law, meaning it springs back.
It springs back when you take a load off, yeah.
Right. If strain varies linearly and stress is proportional to strain through the material's stiffness, its modulus of elasticity, then the stress also varies linearly across the cross-section. Zero stress at the neutral axis, maximum tensile stress on one outer surface, and maximum compressive stress on the opposite outer surface.
And this linear relationship is what gives us that incredibly powerful equation engineers use all the time, right? The Flexure formula.
That's the one. It's a real workhorse. My eye. Or for the absolute maximum stress, SMAX, extensions MT. CI.
Let's break down those letters again quickly. M is.
M is the resultant internal moment at the specific cross-section you're interested in. You get that from your moment diagram.
Okay.
C is the perpendicular distance from the neutral axis to the very farthest point on the cross-section. That's where the stress will be highest.
Farthest point. And why?
Y is the perpendicular distance from the neutral axis to the specific point where you actually want to calculate the stress. It could be anywhere, not just the edge.
Gotcha. And the big one.
I is the moment of inertia of the cross-sectional area about the neutral axis. This I value is purely about the shape of the beam's cross-section. It's not just a number, it's a measure of how efficiently that shape resists bending. A deeper beam, or one with flanges like an I-beam, will have a much larger I than a simple square beam of the same area.
So a bigger I means it's stiffer, it bends less.
Exactly. It can handle more moment for the same amount of stress. And here's a critical so what insight that connects back to geometry. For the internal forces to balance out correctly in pure bending, that neutral axis, the line of zero strain, must also pass through the geometric center, the centroid, of the beam's cross-section.
Wait, so the neutral axis and the centroid are the same thing usually?
For a homogeneous beam in simple bending, yes. It's a huge simplification. Find the geometric center of the shape and bam, you found your neutral axis.
That is helpful. Now, I saw something fascinating in the source material, almost counterintuitive, about adding material.
Ah, yes. There was an example, I think, involving adding ribs to a cross-section. You'd intuitively think adding material makes it stronger, right?
Yeah, definitely. More material, more strength.
But in that specific case, because of how the ribs change the shape, and specifically the moment of inertia I and the distance C, adding them actually increased the maximum stress concentration in a particular spot. The recommendation was actually to omit the ribs in that design. It's a great reminder that intuition isn't always king in engineering. You have to run the numbers using formulas like the Flexure formula.
Wow. So more isn't always better. You have to be smart about where you put the material.
Precisely. It's all about optimizing the shape, which is reflected in that I value.
Okay, we've been talking about nice, simple, straight, uniform beams. But the real world isn't always so neat, is it? What about situations like unsymmetric bending or beams made of different materials, composite beams?
Good points. Things definitely get more complicated there. Let's take unsymmetric bending first. This happens when the beam's cross-section isn't symmetric, maybe like an L-shape or a Z-shaped channel. Or even with a symmetric shape, if the bending load isn't applied neatly along one of its main axes of symmetry.
So like if you load an angle ion beam sideways.
Exactly. In those cases, the simple Flexure formulus, my only applies if you calculate bending about special axes called the principal axes of inertia. These aren't always horizontal and vertical. The engineering solution is clever, though. You figure out these principal axes for the shape. Then you break down the applied bending moment into components acting along each of those principal axes. Then you calculate the stress caused by each moment component separately, using the Flexure formula for that axis. And finally, you add the results together, superposition.
So it's like doing two simpler bending problems and adding them up.
In essence, yes. The formula looks a bit more complex, involving terms for both principal axes, but that's the underlying idea.
Okay, that handles weird shapes or loading directions. Now, what about composite beams? Beams made of, say, wood and steel bolted together.
Right, like timber beams reinforced with steel plates are the classic example. Reinforced concrete. The challenge here is that our beloved Flexure formula assumes the material is homogeneous, the same stuff all the way through. It has one stiffness value, one E, modulus of elasticity.
But wood and steel are obviously very different stiffnesses.
Massively different. So engineers use a clever trick called the transformation factor, usually denoted N. It's simply the ratio of the stiffnesses, the moduli elasticity of the two different materials, say E of steel divided by E of wood. This factor lets you mathematically transform the cross-section into an equivalent one made of only one of the materials.
How does that work? You pretend the steel is wood?
Sort of. You replace the area of the stiffer material, steel, with an equivalent area of the softer material, wood. Since steel is much stiffer, you need a larger area of wood to provide the same resistance. The equivalent wood area would be N times the actual steel area, so the transformed section looks like a bigger wooden beam.
Ah, okay. You create a fictional single material beam that behaves the same way.
Exactly. Then you can find the centroid and moment of inertia of this transformed section and use the standard Flexure formula. But, and this is crucial, When you calculate the stress in the part of the transformed section that represents the steel, you have to multiply that stress value by N to get the actual higher stress in the real steel.
Because the steel is carrying more load for its size. Makes sense.
Precisely. The stiffer material does more work.
And this transformation idea is fundamental for reinforced concrete beams, right? That's a huge application.
Absolutely vital. Concrete is great in compression squeezing, but terrible in tension pulling apart. It just cracks. So engineers place steel reinforcing bars, rebar, within the concrete, specifically in the areas where the bending is expected to cause tension, usually near the bottom of a simply supported beam.
So the steel handles the pulling forces.
Correct. In fact, standard design codes for reinforced concrete often simplify things even further. They just assume the concrete on the tension side of the neutral axis is already cracked and can't carry any tensile load whatsoever. All the tension is assumed to be taken by the steel rebar.
This seems like a safe assumption.
It is, and it simplifies the calculation. So when you do the transformation for a concrete beam, you transform the steel area into an equivalent concrete area. Again, steel is much stiffer than concrete, maybe 8 times stiffer, depending on the grades. So N, as steely concrete, is maybe around 8. You replace the small steel area with an equivalent concrete area that's N times larger, located where the steel is. Then you find the neutral axis of this combined shape, the compression concrete plus the transformed steel area, ignoring the crack tension concrete.
And then you can calculate stresses using the transformed section properties.
Exactly. Find the moment of inertia of the transformed section, use the Flexure formula, and remember to multiply the stress in the transformed steel area by N to get the real stress in the rebar.
Okay, that covers composites. Now for the curveball, literally. What happens when the beam isn't straight to begin with? We're talking about things like crane hooks or chain links or curved arch supports, curved beams where the initial curvature is significant. Our standard Flexure formula breaks down here, doesn't it?
You're absolutely right. It breaks down. For significantly curved games, the assumptions we made earlier don't hold. Most importantly, the strain distribution across the depth of the beam is not linear anymore. It's hyperbolic, actually.
Not linear. Uh-oh.
Yeah, it complicates things. And because the strain isn't linear, the neutral axis, the point of zero strain, no longer coincides with the centroid of the cross-section. It actually shifts towards the center of curvature.
It shifts. Okay, so the whole basis of the Flexure formula is out.
Pretty much. You need a completely different formula, the specialized curved beam formula. It looks quite different, involving terms related to the radius of curvature of the beam's centerline, the radius to the neutral axis, which you now have to calculate separately, and the distance from the center of curvature to the point where you want the stress.
Sounds evolved. Do engineers use this often?
For things like crane hooks, chain links, press frames, yes, absolutely. Calculating that shifted neutral axis location often requires using integral formulas or looking up factors in engineering handbooks for standard shapes.
So is there a rule of thumb for when you must use the curved beam formula versus when the regular Flexure formula is, good enough?
Yes, thankfully there is a practical guideline. If the radius of curvature of the beam's central axis is more than about 5 times the depth of the member, RH5 roughly, then the simple Flexure formula usually gives results that are accurate enough for most practical purposes. The error is typically small in those cases. But for sharper curves, think a tight U-bend or a thick hook where that ratio is smaller. You absolutely need the curved beam formula for safety and accuracy.
Good to know there's a cutoff. 5 times the depth. Okay, next, let's talk about something often hidden but critical. Stress concentrations. You mentioned them briefly. These are spots where the stress suddenly spikes, right?
Exactly. They occur wherever the beam's cross-section changes abruptly. Our standard formulas assume a nice, smooth, prismatic beam, but real parts often have notches, holes for bolts or pins, fillets, grooves, or sudden steps in diameter or width.
And at these spots, the stress flow gets disturbed.
It gets disturbed, yeah. Imagine water flowing smoothly in a wide channel, then suddenly hitting a narrow constriction. The water speeds up and gets turbulent right at the constriction. Stress behaves similarly. It has to flow around the discontinuity, and it gets concentrated, piling up right at the edge of the hole or the corner of the notch. The actual maximum stress there can be much, much higher than what the basic Flexure formula using the net smaller cross-section would predict.
So how do engineers account for this potentially dangerous spike in stress?
They use something called a stress concentration factor, usually called K. It's essentially a multiplier. You first calculate the nominal stress using the standard Flexure formula based on the dimensions of the smallest cross-section through the discontinuity. Then you multiply this nominal stress by the factor K to get the actual higher peak stress, max people K, MCI.
And where does this K factor come from? Is it calculated?
Not usually calculated from first principles in everyday design. These K values are determined experimentally or through advanced computational methods, like finite element analysis. They depend entirely on the geometry of the discontinuity, the shape of the notch, the radius of the fillet, the ratio of the hole diameter to the plate width, things like that. Engineers typically look these K factors up in charts or graphs found in design handbooks and textbooks.
So it's geometry dependent. And when are these stress concentrations particularly dangerous?
They are critically important in a few scenarios. First, when designing members made of brittle materials, think cast iron, some ceramics, even glass. These materials don't yield or stretch much, they just fracture suddenly when the stress gets too high. A stress concentration can easily initiate a crack.
Okay, brittle materials are one case.
Second, and perhaps even more common, is when parts are subjected to fatigue or cyclic loading. That means the load is applied and removed repeatedly, maybe millions of times, like in engine components, axles, or aircraft structures. Even if the peak stress from the concentration is below the material's yield strength, the repeated stress cycles can cause a tiny crack to start at the high stress point and gradually grow over time, eventually leading to failure. This is fatigue failure, and stress concentrations are major culprits.
I remember seeing an example in the source about cracks near window corners.
Yes, window lintels. The sharp corners where the lintel, the beam over the window, meets the wall can act as stress concentrators under bending loads. Over time, especially with temperature cycles adding stress, you can often see cracks initiating right at those sharp corners. It's a classic visual example.
Makes sense. Avoid sharp corners in loaded structures. All right, finally, let's push the boundaries. What happens when the applied moment is so large that the material actually yields? It goes beyond its elastic limit and starts to deform permanently. This is inelastic bending.
Right. We're now talking about stresses exceeding the material's yield strength. Now, here's a key point. Even when yielding starts, experiments show that the strain distribution across the beam's depth still remains linear. The plane sections remain. Plane assumption generally holds quite well, even into the plastic range.
The strain stays linear. That's surprising.
It is a bit, but it's a very useful finding. What doesn't stay linear, however, is the stress distribution. Once the stress reaches the yield strength at the outer fibers, it can't go any higher, assuming an idealized, elastic, perfectly plastic material model. So as you increase the bending moment further, the yielding penetrates deeper into the beam from the outer surfaces. The stress distribution is no longer a simple triangle. It becomes sort of trapezoidal or eventually rectangular as more and more of the cross-section yields.
So the stress pattern changes significantly.
It does, and this leads to the concept of the plastic moment, MP. This represents the absolute maximum moment a beam cross-section can theoretically support. It occurs when the entire cross-section has yielded. The fibers on the tension side are all at the yield stress and tension, and the fibers on the compression side are all at the yield stress and compression. The stress diagram is essentially two rectangles.
The ultimate bending capacity, basically.
Exactly. For a simple rectangular cross-section, this plastic moment, MP, turns out to be 1.5 times my, where my is the maximum elastic moment, the moment that just causes yielding to start at the outer fiber.
1.5 times. That's a significant reserve capacity beyond first yield for a rectangle.
It is. And this ratio, MP-my, has a name. The shape factor, K. It tells you how much additional moment capacity a beam's shape allows it to carry beyond its maximum elastic moment, purely due to the redistribution of stress as it yields. It's a measure of plastic reserve strength related to the cross-sectional shape.
So K equals 1.5 for a rectangle. What about other shapes, like those common I-beams?
Ah, yes. For a typical steel wide-flange beam, or I-beam, the shape factor K is usually much lower, typically around 1.1 to 1.2, maybe 1.14, as one example showed.
Only 1.14. That's way less than 1.5.
It is. What that tells you is that wide flange shapes are incredibly efficient at resisting bending elastically. Most of their material is concentrated in the flanges, far from the neutral axis, where it does the most good in resisting elastic bending, contributing significantly to I. Because they're already so efficient elastically, there's less potential for beneficial stress redistribution once yielding starts. They can only support about 10–20% additional moment beyond first yield before the entire section becomes plastic.
So great elastically, but less reserved plastically compared to a simple rectangle. Interesting trade-off.
It is. And one last thing related to inelastic bending, residual stress. If you bend a beam into the plastic range, so some permanent deformation occurs, and then you remove the load, the beam doesn't just spring back elastically. The parts that yielded try to spring back, but they're constrained by the parts that only deformed elastically. This internal tug-of-war leaves behind a pattern of locked-in stresses within the beam, even with no external load applied.
Stress is left over inside the material.
Exactly. Residual stresses, they can be significant and can affect how the beam behaves under subsequent loading, potentially influencing its fatigue life or its buckling strength. It's another complexity engineers need to consider, especially after processes like cold bending or welding, which can induce these stresses.
Oh, wow. Residual stress, another hidden factor. What an intricate journey through the principles of bending. From just defining beams and their forces through that elegant Flexure formula, then tackling complexities like composites, curves, stress concentrations, and finally, even pushing past the elastic limits. We've covered a huge amount of ground.
We certainly have, and hopefully it's clear just how fundamental understanding these sometimes quite nuanced principles really is. It's essential for ensuring the safety, the efficiency, and the longevity of pretty much countless structures all around us. It really is the hidden language, you could say, of every building, every bridge, every machine that has to stand up to these kinds of forces.
It absolutely is. So for everyone listening, now that you know a bit more about the hidden story of the forces within, how might understanding these bending principles change how you look at the everyday structures around you? From the beams maybe visible in your basement ceiling to the bridges you cross in your commute. Something to ponder perhaps until our next deep dive.